In this video, I'd like to talk a little bit more about the FOIL method for distribution and factoring standard quadratics. And we've already talked a little bit this week about multiplying binomials together. These are some of the most common distribution problems that we encounter at this part in Algebra 2. And we had mentioned that there's a technique called the FOIL process to multiply these together. FOIL is an acronym that stands for first, outside, inside, and last. And if we follow that pattern, we can see that the first two numbers multiply together to make an x squared, or variables in this case, they multiply together to make x squared. The outside numbers multiply together to make a positive 2x. Our inside numbers multiply together to make a positive 4x. And then lastly, our final numbers, our last numbers in each position, multiply together to make an 8. So the FOIL acronym provides us 4 terms as a result of this multiplication, and oftentimes these middle two terms will combine together. Not always, but very frequently they do. And in this case they do. So the x squared had nothing to combine with. The 8 had nothing to combine with. But the 2x and 4x add together to make 6x. And here's our result after distributing and multiplying the binomials together. Please take a minute or two now to try these 3 examples and check your work in a moment after pausing the video. So these are the results, and this example I think works just like the other. It's pretty straightforward and the same as before. The second example, well, we go through the same process, but it was kind of interesting in that they were the same binomial. So essentially this could have started off as a problem that looked like this. X minus 5 squared. That's what generated the x minus 5 to multiply by itself. And in the act of distributing, we got 2 of the same terms here in the middle, and those combined to make a negative 10x. So this is an interesting result, and we actually have a name for it. This is what we would call a perfect square trinomial. And we call it that because of this double number in the middle here producing the 10, and that 5 squared ended up being 25. So 5 squared is 25, and 5 times 2 is 10. So that pattern we call perfect square trinomial. This one at the end is interesting as well because we used the same number 6 in both cases, but we had an x plus 6 group and an x minus 6 group. So they're not quite exactly the same, but the end result here is interesting too, because in the outside product and the inside product we ended up getting 2 different 6x's, but one was positive and one was negative, and they effectively canceled each other out. And with them gone, we don't have a middle term reported. Now, sometimes we would call this x squared plus 0x minus 36 because the 2 terms in the middle added to equal 0. But to be honest, we usually don't show this middle term, and we leave it in this format here in the box. Now, this format here also has a special name. We call this one a difference for subtraction of 2 squares. We'll talk more about those at another time, but difference of 2 squares is the name for this particular result. We sometimes abbreviate that dots, by the way. Difference of 2 squares. So if we wrap up the multiplication process here, we can summarize that with a couple sentences. The process used to multiply polynomials requires multiple distributions. We have several multiplications. And in particular, when 2 binomials are multiplied, when we have 2 groups of 2 multiplied together, only 2 distributions are needed. So there's only 2 distributions from the first group into the second. And so that's where the acronym FOIL came into play. We use the acronym FOIL to remember the steps of that distribution. Now our goal with foiling and even larger distributions is to end with a polynomial that's written in standard form. talked about standard form in class. That's where we have all of our terms combined, all of our like terms combined, and we would report our resulting monomial terms in largest exponent in decreasing order. So we had an x squared, x to the first, and we even talked about x to the 0 power being a placeholder at the end here. And we can see the exponents have now decreased. Now, solving polynomial equations is a little bit different. So solving polynomial equations is a little bit different than just distributing and multiplying binomials together. When we multiply binomials together, that's an act of simplifying. Here, if we're actually solving an equation, a lot of times we actually want the answer in factored form. And factored form is essentially what we had started with. So if we've got expressions that are already in factored form and they show up as part of a larger equation, then we're in pretty good shape. But oftentimes we'll actually begin with the standard form. We'll actually have these answers here that start our problem, and then we have to work backwards to find the factor groups. Now, as long as we recognize that our standard trinomials take on this format when all like terms have been combined, then we can utilize this pattern to help us with some rules moving forward. So when a trinomial is simplified and all like terms are combined, we'll have an x squared term with a coefficient in place of this letter a. We'll also have a coefficient b in front of the variable x, and then we'll have a coefficient or constant c at the end of the trinomial. Now, all trinomials of this of quadratic form will have an x squared term. If we don't have a number written in front of x squared, if there's nothing written there, we're going to assume that that number is 1. However, all quadratics do not need a b or a c value. If there's no number written in front of a term x, we will assume that it's 1. But if there's no term here at all, if it's completely gone, then we assume that b is equal to 0. And that's possible. Similarly, if c wasn't written whatsoever, we'd assume that c was equal to 0. Now, if c was equal to 1, that would have to be written, but again, sometimes the letter c is not included. We'll call that 0. So the general rule is this: if I'm starting with an expression that looks like this is written in standard form. We have an a, b, and a c value. So a is here, unwritten, so we'll assume that it's equal to 1. We have a b value that's here, and a c value that's at the end. We'll include the negative sign with it. So we have an a, b, and c value. The procedure for factoring a standard trinomial when a is equal to 1 is to find factors of c, so factors of 15, that add or subtract equal b. So in class I had mentioned that we can write the number 15 and start reporting its factors. One of the tricks that I like to use is I write the smallest factor and the largest factor of 15, the largest and smallest number that goes into 15, and then I work my way inward from there. The next largest number that goes into 15 is not 2, but it ends up being 3. And 3 times 5 is what gets me back to 15. So I know that 5 is a factor. So as I continue to move inward, the next factors would have to live somewhere in between 3 and 5 if they exist. But the only number between 3 and 5 is the number 4. 4 doesn't go into 15. So I think we've got ourselves a pretty good list here. So the goal now is to find two numbers that multiply together to make 15, so a pair of numbers that are in this factor grouping that also add or subtract to equal 2. And hopefully you recognize that a 5 and a 3 can be used to combine to make a positive 2. We would just need a, let's see here, a positive 5 take away 3. 5 minus 3 is what would get us to positive 2. So with that known, the factor form takes on this, the factored polynomial takes on this form. We're going to start with x and x at the beginning. We always start with our letters at the beginning if a is equal to 1. And then we just report the two numbers that we use to complete this factor, positive 5 and a negative 3. And this factor grouping would FOIL back together to make x squared plus 2x minus 15. We can check that real quick. The first two terms multiply to make x squared. The outside terms multiply to make negative 3x. Inside makes a positive 5x. And the last two terms makes a negative 15. Combine the like terms in the center, and we're left with x squared plus 2x minus 15, which matches what we started with. Now, we don't have to do this step all the time. This is just shown here as a check to verify that this answer was the correct one. We would stop at the factored result. We don't need to FOIL them back together unless you're performing a check. So here's another example. Again, we're going to start with the C value here because I noticed that my A value is 1. And so starting with the C value, we just need to find numbers that multiply together to make 45 that add or subtract to equal negative 4. So my process is to write the smallest and the largest factor, 1 and 45. 2 does not go into 45, but I know that 3 does, and 3 times 15 would make 45. The next factor pair would have to exist between 3 and 15. I don't think 4 works, but 5 does. 5 times 9 makes 45. And if there are any more factors, they'd have to be between 5 and 9. So that would be 6, 7, or 8. None of those work, so I think we've got our entire pair, or entire list of factors, I should say. So which of these pairs would add or subtract to make 4? Well, I think that's this group here in the middle again, 5 and 9. And we don't always utilize these numbers that are in the middle, but twice now we've seen that the numbers that we need to answer our question come from the center of our factor groups. So that's a convenient coincidence. Now as we proceed from here, I'm going to use a, let's see here, let's take a positive 5, but a negative 9. Positive 5 and a negative 9. Those two numbers would add together or subtract to make the negative 4. So I think that would be a good choice. As far as our factored result goes, since this is a standard trinomial with a equal to 1, we always use the letter from the problem, our variable in the problem, to start our factor groups. And we would use these two values that we settled on, positive 5 and negative 9, as our result. So our factors are x plus 5 and x minus 9. Again, we could check this using a FOILing process to see if it ends up equaling the x squared minus 4x minus 45, and you can do that on your own if you would like. Let's take a look at these last two examples. In this first case, we had only two factors for the number 19, so we had no other options but to utilize them. And as it turns out, a positive 1 and a positive 19 add to make 20. Also, that 1 times 19 multiplied to make our positive 19. So our factor pairs ended up being x plus 1 and x plus 19. In the last group, it was kind of interesting. There were several factors to the number 16. None of the pairs, 1 and 16 or 2 and 8, would add or subtract to equal 8, but as it turns out, 4 times itself equals 16, and 4 plus itself ends up equaling 8. So the end result here, being x plus 4 and x plus 4, is a nice solution. Now there are times that we'll take this answer, since it's an expression that multiplies by itself. There are times that we'll report it this way, x plus 4 squared, and that would be okay as an answer too. So be on the lookout when you're working on Math Excel this week, especially on questions 10 through 15. The instructions should tell us exactly what format we should be in, and whether it needs to be two separate binomials or if we should write it as a single binomial with a power of 2. Now moving on from here, there are also problems that we're going to see where we have a standard trinomial that a is not equal to 1. Now I should note this, that sometimes we will see trinomials that have an a value not equal to 1, but they might have a GCF, or a common factor, amongst the three terms. So I'm going to make a note here that we're going to say that this is a procedure for standard trinomials where a is not equal to 1 after we check for GCFs. We talked about this in class. A GCF, greatest common factor, allows us to reduce the size of each of our terms by factoring out a common factor, numerical factor. And a lot of times, or sometimes I should say, that will reduce our standard trinomial with a not equal to 1 into one that does have an a value equal to 1. See me for some clarification on that, or I'll create another video with a few extra examples for you to look at. Now, since our a value is not equal to 1, and in the foiling process our first terms multiply together to equal our first term of our polynomial, we can't just rely on our c value anymore. So the instructions here, the procedure would be to look for both factors of a and c, and we're going to have to guess and check factors in their combinations that would FOIL together or distribute together to get us back to the b value in the center. And let me show you what that looks like, and I'll talk more about the hint in just a second. So I'm going to write down the number 12, and I know its factors are 1 and 12. We've got 2 and 6, and we've got 3 and 4. Lots of factors to the number 12. We also have to look at the factors of 5. Those are just 1 and 5. So as far as our factored process goes, we have to pick a pair of numbers that multiply together to make 5 and a pair of numbers that multiply to make 12. Now we don't have any real choices over here to make the 5, so I know that I have to use 1 and 5 here. But I do have several choices in the number 12. Now the hint says that the factors that are close to one another are often the best choice, kind of like what we saw back here. The factor pairs that were close to one another in this group, and even this last one back here, those were all used to answer the problem. So I'm going to start with a 3 and a 4 to begin with. Notice I'm calling them 3x and 4x, however, because it's a 3x times 4x that needs to multiply together to make 12x squared. So if 3x and 4x is my first guess, this is my check that has to be done. I know that 3x and 4x makes 12x squared, and I know that 1 and 5 multiply to make 5. But what I don't know in the foiling process is if this outer product and inner product will FOIL back together to make 23. So here's how I check that. I draw these little boxes, or these connection lines here, and I note what the multiplication would be. In this case, 3x times 5 is 15x. And I note that 1 and 4 multiply to make 4x. And I ask myself, will 15x and 4x now combine to make 23? This is what would happen in our foiling process. I have no way, or I do not see a way that 15x and 4x will add or subtract to make 23. So unfortunately, we can't use the combination that we guessed just a minute ago. So the 3x and the 4x is not a good choice. What if I tried 4x here and 3x here, however? It's going to change things a little bit. The 4x times 5 does make 20x, and the 1 times 3x makes 3x. Well, now I'm at a position where I could combine to make 23x. I need a positive 20x and a positive 3x to make 23. And the only way that I can get a positive 20x in this multiplication is if I had a 4x multiplied by a positive 5. And the only way that I can get a positive 3x is if I take this 3x and multiply it by a positive 1. So with that guessing and checking method, we've now been able to establish the factor pairs of this polynomial. We could FOIL this back together and check our work just like we did with our other examples. Let's try another one. Now in this case there is a GCF. Each of these three terms can be divided by 5. So I'm going to start with that first and see what happens next. So with 5 factored out of the way, I'm still left with a 5x squared, a minus 7x, and a minus 6. There are no other GCFs, numerical GCFs in this group. So I have to work with it as it is. I think this would be a good guess and check standard trinomial where a is not equal to 1. So I'm going to ignore this 5 for the time being, this coefficient of 5. I do want it as part of my answer set, but it does not affect the factor groups that I'm about to investigate. The 5 that I'm writing down here comes from the leading term in the trinomial, and the 6 that I'm writing down here is the trailing term, or the constant term. Factors of 6 are 1 and 6, and 2 and 3. Factors of 5 are 1 and 5. So just like we saw before, 1 and 5 only has a pair of factors, so I know I have to commit to a 1x and a 5x in this group. Don't necessarily have to write the 1 here, so x times 5x is what would multiply to make 5x squared. But I've got different choices to make here with the 6. As I suggested, I'm going to try by picking two numbers that are close to one another first and see where that gets me. So I'm going to guess with the number 2 and the number 3. I'm just going to place those here as a guess, and I'm going to check. X times 3 gives me 3x. 2 times 5 gives me a 10x. And I think we've actually made a pretty good choice. Can 10x and 3x combine to make the middle term negative 7x? The answer is yes, of course. If we had a negative 10x added with a 3x, that would combine to make a negative 7x. So the only way that I can get this variable x and this number 3 to multiply together to make a positive 3x is if this was a positive x multiplied by a positive 3. And for this middle term here, we've already kind of committed to a positive 5x here, so I'm going to leave that alone. But this positive 5x times a negative 2 would get us to a 10x. And now we've got this polynomial factored into its groups. Now this video is starting to get a little bit lengthy here. I'm going to go ahead and stop this one and pick up with a second video for the back half of the page. But I would like to note that on our homework this week we have around 20 or so questions, and I think our discussion so far should get you through number 17. Pay close attention to these standard trinomials where a is not equal to 1. Those start popping up towards question 16 or so. And try using this technique to complete that work. You can also use the help tools. Don't forget that they're available, and you can also reach out to me for extra help too. Please let me know if you're stuck. I'll catch you in the next video. Thanks for watching.